Okay, let's just start the slideshow here, see if this works. All right, well, so we're talking about motion, and we should talk about how mass is different from weight. So you probably know this already, but mass is the amount of matter in an object, but weight is the force that acts upon that object. So for instance, if you were standing in an elevator, right, and so the elevator is just sitting there, hasn't started moving yet, then let's say this little guy here weighs 140 pounds. Now as the elevator starts accelerating, you kind of know that from being in elevators that you feel a little heavier, right? And so you can see the scale goes up as this elevator goes up, so the weight changes because the force is now different. The elevator's floor is exerting a force on you to accelerate you to the speed that the elevator has when it's, the elevators usually, depending on how far they're going up, will accelerate to a constant speed, then go for a constant speed, and then decelerate. And you've probably felt that, especially on fast elevators. And in this case here, the accelerator is coming down, so you get in the elevator and you're going to go down, and it accelerates downwards, and that makes you feel a little bit lighter. That's that same feeling that when you're going over a hump in a roller coaster, you get that feeling like your stomach is sort of floating up on your right inside you, and it's kind of an scary feeling, I guess, depending on your inclination, you like roller coasters or not. So it's that same feeling, get a little lighter. Now let's imagine if the cord broke and you're in what we call free fall, right? You're not going to have any weight. Okay, this is free fall, right? So I think I remember when I was a kid, I used to think, well, you could just, if the elevator's um, falling, you could just jump right at the end and then you wouldn't crash into the floor. But in fact, you would be in free fall. You're literally falling, and the elevator's falling as well. And so, depending on how far you're falling, you would most certainly die. Okay. Now, the question here is, why are astronauts weightless in space? There actually is gravity in space. You have to go very, very far away from the Earth for there to be really zero gravity. They're weightless because they're in a constant state of free fall. It's like they're in that elevator with the cord cut, right? Because what's happening is that, and here's a nice little example of that. If, let's say, you put a very high diving board and you've just walked off of it, well, you would fall and hit the Earth. During this whole time, you would be in free fall, right? And it may not feel like free fall because there would be lots of air resistance, etc. Just like when you're jumping out of a plane. I don't know if any of you've done that, but there's a lot of air resistance and air blowing past you, and it may not feel like it looks like it feels when you're weightless in the International Space Station or something, right? But that's only because there's a lot of air. So let's just pretend there's no air. So while you're falling, it would be just like you were in the space station, right? Except for you're about to die. And if you go a little faster, you can see you fall a little further out before you hit. Now, if you go just fast enough, and I wish they hadn't put the little rocket on here, I would just imagine the person can run that fast, you're going to keep falling, but you never hit. And that's what an orbit is. And so you're literally in free fall the whole time, say you're in the International Space Station, because it is falling, but it's falling fast. It's going fast enough that even though it keeps falling, it never hits the ground. So that's what an orbit is, and that's why the astronauts are weightless in space. It's not that there's no gravity. There certainly is gravity. And it's really because you're falling the entire time. So that's a comforting thought. Okay. Let's watch a video about Newton, because that is our next topic, our next person to talk about. So remember that Kepler, who figured out what the orbits look like and his three laws, etc., and Galileo, who really solidified a lot of the things we know about motion, like acceleration and the acceleration due to gravity being the same for all objects that fall, etc. They put a lot of new information out into the world, but no one had really sort of gathered that information all together, and certainly not when it came to what was causing the planets to go around the sun, what was holding the planets in their orbits. People knew there was this thing called gravity, that when you dropped a ball, it would fall to the ground, right? But understanding that was the same thing that was making the moon go around the earth and the earth go around the sun, etc., was a big leap. So this is why we need to talk about Newton. Okay, let me see.
Newton was a towering intellect. It is astonishing what he did. His moment in the history of science is a sharp break in which the power of mathematics is really brought to bear on aspects of the physical universe. He is what set us down this path of using mathematics to describe the universe, showing that math, for some reason, is the language of the cosmos.
Kepler observed through his data the attractive effects of the sun. It acted like a giant magnet. Might the planets also be like magnets? Galileo had theorized about the rate of acceleration of falling bodies, and he realized that regardless of their mass, falling objects always fall at the same rate. But years later, Newton had something to add to Kepler and Galileo.
The great insight Newton had was to bring Galileo and Kepler together and to realize that the things that make projectiles move and fall on Earth is the same thing that makes the planets go around the sun in the skies.
In a sense, the planets are falling toward the sun, just as Galileo's falling bodies fell towards the Earth. The crux of it all is gravity, the strange action at a distance that holds everything together. Newton didn't just observe gravity. He drew it up as a provable equation, showing that gravity was the energy, the tether, that kept matter, objects like the Earth and the planets, from flying headlong into interstellar space. Gravity, the attractive force that affects all matter in the universe, gives the universe order, and gravity is described by the science of physics.
Newton created physics. He was the person who first saw the fundamental laws underneath all of these observations. Newton's laws explained almost everything.
Newton postulated the laws of motion, the universal rules of gravity. He begins a new era in science, using observations and mathematics to describe the laws of nature.
He could, in fact, show that the rate at which an apple was falling to the earth was directly related to the way the moon was falling around the earth. Because he understood that the same laws that led to the motion of the planets around the sun led to the motion of the moon around the earth.
Newton's great book, the Principia, revealed that the tides, the velocity of orbiting planets, even the shape of the Earth could be explained through the pull of gravity, because everything with mass exerts a pulling force on everything else with mass. The moon pulls the oceans. The Earth pulls the moon. The sun pulls the Earth. And the closer these objects are to each other, the stronger gravity pulls. Newton's Principia is such an engulfing work of genius that it almost makes up for one disconcerting fact. Although Newton formulated the laws that govern gravity, he never explained or even understood why it works. And gravity, when you think about it, is bizarre.
Understanding how the earth knew where the sun was to go around it. What happened if the sun suddenly moved? What would the earth do? This action at a distance is something which he gave up on. He said, I'm just not going to worry about that question because the laws work.
Although physicists still struggle to define gravity, Newton had gone far in revealing it. 200 years later, Albert Einstein would rival Newton's genius, not only creating new laws of physics, but reinventing the universe.
Okay, so as they say in the video, Newton really came up with this idea that the same thing that made objects fall on the ground, made projectiles that you shot out fall to, go far then fall to the ground, was gravity, and of course was the same as the force that was keeping the planets in orbit around the sun, the moon in orbit around the earth, etc. Now in the end of the video they mentioned that there was this interesting problem that Newton ignored about what would happen, let's say, if the sun all of a sudden disappeared. How would the Earth know to stop orbiting and to just go off into space because it no longer has that tether? Well, it wasn't until Einstein came along and reformulated the theory of gravity, and we'll talk about that later in the course, that was resolved. So we will talk about that at some point. Okay, so just as a summary, how did Newton change our view of the universe? Just to give you a little history here of him, he was an amazing intellect. Strange guy, but an amazing intellect. So in 1661, he goes to Cambridge, so he starts college at 19, normal age. Now, the interesting thing is, of course, lots of bad things were happening at that time. So, for instance, there was the plague, the bubonic plague that came to England, and he fled Cambridge 4 years later because of the plague. But during his time away, he invented calculus, discovers the universal law of gravitation, develops laws of motion, and begins optical study. So he didn't waste any time messing around because he had to leave school. And during that 4 years, he did all of that, and then in 69, he became the Lucasian Professor of Mathematics. He invented the reflecting telescope, which is the type of telescopes we use today. We'll talk more about what that means later. He publishes his book, The Principia. He has a nervous breakdown. He becomes the warden of the mint, which is odd because mint is where they made money. It's a little strange that he became the warden of the mint, but he did. He published another book called Optics, all about optics. And he was knighted in 1705. But not for scientific contributions. So a really interesting dude. One of the things that he is said to have said on his deathbed is that his proudest achievement was that he died a virgin. So strange guy, for sure. But no disputing his genius. Okay, so Newton, sort of one of the most famous things that he's did besides gravity is really define motion. And by define, I mean he came up with 3 laws that govern motion, and we're going to really study these in detail. So his first law of motion was something that Galileo talked about as well, and the idea is that if you have an object that's moving at constant velocity, and constant velocity can also mean 0 velocity, so at rest as well, it will stay moving at constant velocity or at rest unless a net force acts to change its speed or direction. We know that already. We were just talking about that, but that's his first law of motion. It's often called the law of inertia, right? So if something is sitting at rest, you have to push on it with a net force to get it to not be at rest anymore. But it's also true of a constant velocity, right? You have to change that velocity, as we know, you have to have a net force. Second law of motion tells us that the force that you need to accelerate an object is proportional to its mass. And that's given up here, as you can see. Force is mass times acceleration. So if you want a particular acceleration, you have to give a force that's equal to the mass of the object you're trying to accelerate times that acceleration. Okay? So this is one of those things you learn in the very first, almost the first day of physics class. Very important law used for everything that, all of kinematics, which is the study of how things move. Okay, and then there's a third law. This one I think gives students trouble, so we'll go over this a bunch. For every force, there's always an equal and opposite reaction force. Now this one's a little tricky because you have to think about what the forces are acting on. And so I'm going to go to our blackboard and we're going to kill that, get a new layer here. Get rid of that layer. Okay. So let's think of a situation where you have, say, a little block and you're trying to move it. So here's our little block. This is kind of like that moving the file cabinet simulation we had. And it's sitting on a table here. I know that doesn't look like it's very flat. But think of the table has a little friction. So imagine you're trying to move your heavy book across the floor or across your table. And you're going to push on it this way. And I'm going to draw that force sort of pushing this way. So this is the force that you're exerting. So you're pushing your hand's touching the book here, and it's pushing this way with this amount of force. And I'm going to put that as F1. Well, the book is actually pushing back on you. So let's draw, let's see, this little dot represents your hand. The book is pushing back on you with exactly the same force. Okay, but in the opposite direction. So we would write that as, F1 is equal to minus F2, right? It's because if this is the positive direction, this is the negative direction. And they're equal and opposite in magnitude. So magnitude means the length of the vector. How strong is the force? So as I push on the book, it's pushing back on me with exactly the same magnitude force. Now you might go, well, wait a minute, how does the book move then? But you got to remember that these reaction pairs, so they call these reaction pairs. So Newton's third law is about reaction action. You might have heard this before. Reaction pairs. So when I push on the book, it pushes back on me. So the reason that the book moves is that the only thing that matters to whether the book accelerates or not is the net force on the book, not any forces on me. So when I push on the book and the book pushes back on me, these forces are acting on two different things. This acts on the book acts on me, right? So this is me or you, I suppose. You were the one pushing, I think. So just to be very clear about that, it's a little hard to get your head around, but that's what happens. So, and you're not used to thinking about that, but that is the case. All right, so you'll get used to it, I think. So let's go back to the PowerPoint. Okay, and that's Newton's third law. For every force, there's always an equal and opposite reaction force. But remember always, those two forces are acting on different objects. Okay, all right. So here's a question that this is exactly what we were talking about, Newton's third law. How does the force that the Earth exerts on you, gravitational force, of course, compare with the force that you exert on it? Let's see, Earth exerts a larger force on you, or you exert a larger force on Earth, or you and Earth exert equal and opposite forces on each other. Well, in fact, it's C, right? You may not think that you exert a force on Earth, but you do. All objects with mass attract all other objects with mass. And as we'll see when we look at Newton's equation for gravitation, that it depends on the strength of the force depends on the two masses, but they're equal and opposite. So the Earth is pulling down on you, keeping you tethered to the floor, right? So you're not floating away. But you are pulling back on the Earth with exactly the same force. The reason the Earth doesn't move to come up to your feet, say if you're sitting on a stool and your feet are above the ground, is that the Earth is so much bigger than you. And there's Newton's second law to think about, right? F equals ma. And if you want to accelerate the Earth towards you, you got to put a huge force on the Earth. Okay, so, but it is equal and opposite. The force that the Earth exerts on you and the force that you exert on the Earth. Note that these two pairs of forces are acting on two different things. The force due to the Earth on you acts on you. The force due to you on the Earth acts on the Earth. Two different things are being acted on, but with forces that are equal and opposite. Okay, here's another question. I push on the wall with a given force. The wall pushes back on me with an equal force. This is a statement of, well, law number 3, right? Newton's third law. Okay. Now let's talk about, sort of get into the nitty-gritty of Newton's universal law of gravitation. And this is what we mean when we say that he figured out that the tether that keeps the moon going around the Earth and the Earth going around the sun is gravity. He came up with his universal law of gravitation, which tells us exactly what the force is between two objects. Okay, because remember, every object with mass attracts every other object with mass. So if you have two objects with mass, they're going to attract each other. And this is the equation that tells us about it. There's the force. How big is the force? Is equal to this gravitational constant, g, times the mass of the first object, times the mass of the second object, over the square of the distance between them. So let's look at a simulation that might help us understand this a little bit. Okay. All right. Here we go. So we have two people holding onto these masses because they are two masses and they are attracting each other. And here's the force. Now we measure forces in newtons. You don't really need to know that, but you can see it's a very small number, 0.0000012025452 newtons, right? Small number here because the masses are relatively small. Now, if you were really holding these two masses with 447 kilograms apart from each other, you wouldn't be able to feel the force. It's a very tiny force. You have to be super careful to actually get masses that small to measure the gravitational force between them, and people have done that. But you certainly wouldn't be leaning back because it's so heavy or something, right? Or the force is so strong. But let's take a look. So we have two equal masses here, right? Mass 1 and mass 2 are equal. And notice that the force on mass 1 by mass 2 is the same number, the same magnitude, right, as the force on M2 by M1. Notice, same exact number, right? Okay, so what happens if I change, oh, and these are not the same forces because I messed that up. Let's go back and do that again. There we go. Okay, but notice that the number changed, but for both of them, right? Both of them have the same force because there are equal and opposite force pairs, right? The force acting on M1 due to M2 is this number, but the force acting on M2 due to M1, the gravitational pull of M1, is the exact same number, so the same magnitude force, but in opposite directions. M2 is trying to pull M1 towards it, see? This is the direction of the force. And M1 is trying to pull M2 towards it, right? See the direction of the force here. Now let's notice what happens as we bring these two closer. So we have the same mass, M1, M2 the same. And let's see what happens. What's happening to the force? It's getting bigger. Look at the size of the arrows if you don't want to look at the numbers. When we're getting close, the arrows get bigger because the force gets stronger. Remember, the closer you are, right, stronger the force. That's that in the equation we saw. Let's see if we can just move this over so you can see it right here. You can see that it's inversely proportional to the distance between the two. So as the distance gets smaller, the force gets bigger. Okay. All right, let's take them apart and see what happens. Of course, we're going to get much smaller forces as we move them away from each other. Okay. Much smaller forces. Look at those little tiny arrows. But again, the forces are the same in magnitude. This one is exerting the force on this one that is the same in magnitude as the force that this one's exerting on this one. Okay? All right, let's see what happens when we change the mass of one of them. Let's change this guy's mass. I'm just going to make him really big. See how it's getting a little darker? That means it's getting heavier. Okay. Look at the arrows got bigger because as I change the mass of one of them, the force gets bigger. But the number, the fact that they're the same, right? The force due to M2 on M1 and the force due to M1 on M2, the number's the same, right? Equal and opposite. But it got bigger because I'm making M2 bigger, all right? So I hope you can see that here, right? If I make M2 bigger, the force gets bigger. So it's directly proportional to the mass of M1 and M2, right? So again, I can now make M2 bigger, right? And I get a bigger force, or I make it smaller, and I get a smaller force, right? Okay. All right. All right, so let's remember that forces have strength and strength, right? Which we call magnitude. So how strong is the force? How hard are you pushing or pulling? And direction. And that if we want to get the net force, we have to add and subtract those arrows, those vectors. So let's go and take a look at a simulation about how to do that. We've done it. We did a little bit on the blackboard, but we'll be a little bit more careful about it here. All right, so this is another simulation. And I can grab a vector. Let's say we have a force. Let's say that you're pushing on your car because it ran out of gas with this much force, okay? And your friend is pushing in the same direction, but less force, not as strong as you. What is the net force that you're both exerting on the car? Well, we can show the sum, which is given by just adding the two, sort of tail to head. Oops, that's not what I wanted to do. Okay, I wanted to move you. Okay, so if I put this one like right here, notice that I've added your force to your friend's force and get the net force, right? Okay, let's use the same example here. Go away. You need to go bye-bye. All right. And so you're pushing on your car to the right, but your friend decides to be mean and pushes on your car to the left. Let's say he gets a couple of friends and he pushes to the left just to be mean. Now what's the net force? Okay, how do we figure that out? Well, we take our vector and we sort of lie them tail to head. So this is the tail to the head of this one, and then we figure out what the leftover is. And look what that leftover is. Right, you can tell. Look at the leftover. It's that much is left over. So the net force is this much. So your friends are going to win. They're pushing your car in the opposite direction away from the gas station. Right? So we add vectors in this way to figure out what the net force is, because sometimes we have more than one force, right? Like you pushing your cars and the other friends pushing the car in the opposite direction, or being nice and pushing it in the correct direction with you. So do we add forces by sort of adding these vectors, these little vector arrows, tail to head. Okay, so let's go back and we'll try an example. So let's say that we have two planets here, and that they have the same mass. Okay, kind of like that example we had where we had the same mass on that simulation. And we have a little spaceship or a little moon or something right here between the two. And now we want to figure out what the forces are due to the two planets at different places. So let's look right here at this place. What is the force due to M1 on this little guy? Well, we could, decide that M1 had a particular mass and that the little white ball had a particular mass and actually calculate a number. But we're just going to draw an arrow and just say, okay, so let's say it's something like that, right? We know that it's going to be towards M1. That is the force on the little white ball or the spaceship, let's say. How about we just call it a moon? So the force on the moon due to M1 is that arrow, because M1 is going to try to pull that moon towards it, right? Okay. What about the force on the moon due to M2? Well, M2 also wants to pull the moon over, doesn't it? So I'm going to consider that force in green. Now, why is it smaller? Because the moon is a lot farther away from M2 than it is from M1. So it's going to be smaller. And remember, M1 and M2 have the same mass. Okay. All right. Now, what is the net force? Well, wrong direction. I have to add tail to head. Look at that, see? Tail to head. And then I get what's left over, okay? What's left over is this net force towards M1. I could have put it down here, but it doesn't matter where you put it, right? So the net force is towards M1. So if someone's holding this moon here and then lets go, the moon is going to start accelerating towards M1. Because it's feeling a net force towards M1. Okay, let's try another example. Let's say the moon is here, in between, right in the middle. Okay, there's the force due to M1 on the moon. And notice that this arrow, I drew this arrow smaller than this one, because the moon is now farther away from M1 than it was in this case. Okay, so smaller force, right? The farther away they get, the smaller the force. Okay, and now, what's the force due to M2 on the moon? Well, it's going to be exactly the same length, right? as the force, the blue arrow, which is the force due to M1, because M1 and M2 have the same mass, right? Now, what is the net force? Well, we have to add them tail to head and feel like what's left over. Let's see, tail to head, is there anything left over? No, because these two are the same size and they're in opposite directions. So we have net force of 0. So if the little moon was sitting right there and someone was holding it and they let go, it would just sit there because it doesn't feel a net force. Okay. All right, let's try another position. What about here? Okay, well, the force due to M1, the blue arrow, is of course still, M1's still trying to pull the moon in that direction, right? So we know the direction, and it's smaller than here, right? Because the moon got farther away. What about the force due to M2? Well, it got bigger because now the moon is closer to M2, and the way I've drawn this is the same distance from M2 as this one is from M1, so those arrows should be the same, although I don't know if I did that correctly, but they should be the same. In my setup, should be the same length arrows here. But again, this one has a stronger force on the moon than M1 because the moon is closer to M2 than it is to M1. Okay, so how do we get the net? Well, we add tail to head, so here's our head and tail, figure out what's left over. Okay, well, we have more of the green, and that goes in that direction, so the net force is towards M2. So if I let go of the moon here, it's just going to start accelerating towards M2. Okay, hope that was clear. Let's try some on your own. Well, we actually do a few questions, then you can try one on your own. All right, so we all have mass because we're all made of matter. What gravitational force do we most often interact with most strongly? Okay, the force between nearby people, because other people have mass too. And everything with mass exerts a force on everything else with mass. So you and your friend both exert gravitational forces on each other. They are quite small, in fact, not really measurable, but you do. The force between us and the sun, meaning the force between you and the sun, or you can even think of it as the force between the earth and the sun. Okay, well, yeah, there is that force, but do you really interact with it most strongly? Not really. But our weight, which is a measure of the gravitational force between us and earth, that you definitely feel, right? You feel that all the time because you're not floating away. You feel that when you gotta hike up some stairs, right? Okay. So this one is definitely the one you interact with most often and most strongly. Okay, here is your question that you need to pause the video and answer.